So, good afternoon to everyone. My name is Venanzio Giannella, and I am a researcher at University of Salerno in Italy. Today, I'm going to present you one of our activities we have on additive. In particular, this activity is in collaboration with is based on the usage of the electron beam belting technology, and is based on the fatigue regrowth behavior of a widely known material that is the titanium alloy, the Ti6Al4V. So here there's a quick outline of this presentation. So the purpose was to assess the main fracture properties of EBM additively manufactured titanium alloy. And basically we we are developing right now an experimental campaign that comprises the typical passages of manufacturing the samples, then manufacturing the specimens, and then instrumenting the specimen, and then the fatigue regrowth tests. Today, I wanted to add to this presentation also the ongoing activities that we are currently doing in this regard. And at the end of the presentation, we are going to see, to have a quick look at the results, brief discussions, and then conclusions. So for what concerning the printing setup, as I said before, we considered the EBM technology to manufacture the specimens. This is an Arcam Matrix machine that is available at the Italian Aerospace Research Center. These are the main specifics of this machine. And at the bottom left corner of this slide, we can have a quick look at the chemical composition of the powder that we use it for the manufacturing. So from the manufacturing, we prepared a total of 54 samples that we equally subdivided into 27 samples for the fatigue regrowth tests and 27 samples for the quasi-static tests, so for evaluating assistance, the K-critical. If looking at the fatigue regrowth tests, these were 27 subdivided into 3 building directions, so 9 specimens per each of the 3 building directions. And they were 9 because of 4 specimens that were tested in air condition, in laboratory condition in air. 4 specimens were tested in a corrosive environment, and 1 was a spare specimen that was used for the calibration of the machine. The holes for the pins and the notches were made by EDM after the manufacturing. This is a close-up of one of the specimens where I wanted to highlight the front face and back face for the reasons we will see in this presentation. These are just some photographs of the samples as coming from the manufacturing. I wanted to highlight the building direction for your better comprehension. I want also to underline that the specimen labels that we see in these photographs are always positioned on the front end face, so the face where the notches were made. These are the photographs for all the building directions. For what concerning the test setup, we started from the as-built sample, and then we manufactured the specimen. So we created the notches and the pins. Then we instrumented the specimen, and we can see in this central figure that we considered 2 measurement systems. One is based on a Craig gauge glued on the side of the specimen. Another measurement system is based on a strain gauge that is positioned at the back end face. These sensors, the one on the right side, allowed us to measure the strain during the process. With this strain, we were able to calculate the actual crack length during the propagation. This is a figure of the specimen that was ready to be tested. We can see also that we considered a clip gauge as a further element of comparison. The machine that we used to test specimens was an instrument machine, was a servo-hydraulic testing machine that can be used for static and cyclic tests. that was equipped at that time with a load cell of 20 kilonewton. The actual maximum load that was applied to the specimen was around 6 kilonewton, and the load ratio was 0.1. So here we can see a figure of one of the fractured specimen. We can appreciate the typical mode 1 propagation. This was observed for all the specimens. This was rather expected for being the specimen loaded in pure mode 1. We considered a pre-cracking of 2 millimeters, so we discarded the first cycles up to a crack length of 2 millimeters. Then we started the so-called cycle counting. Here there's a comparison of the crack length versus the number of cycles for the two measurement systems. We can appreciate a very good agreement between these two observations. We can say that with the back phase strain, as I said before, and through the formula that I reported at the bottom right corner of this slide, we can, starting from the epsilon measured at the back phase, we can derive the actual crack length. So it is a different measurement technique. And we obtained a very good agreement between, let's say, more traditional measurement system. So going on to a comparison between among multiple specimens, we concluded with this chart. Here we can see that the specifics of this curve. So we can see that the green specimens were those specimens that provided a slightly better fatigue life, so longer, even though it has to be admitted that I was expecting personally a slightly larger deviations between the curves. So as I said before, this is an ongoing activity. We are currently performing, we're currently going on with this activity, and precisely now we are performing fatigue regrowth tests in a corrosive environment. So this is a photograph of the test setup that we in-house made, that we have in-house made in our university. This, to be honest, it is a photograph of a specimen made of steel additive manufactured, but still not titanium. This is a close-up of the specimen, where we can observe the water that is continuously flowing through the tests. This is an in-house made box made of with additive, so it is PLA. There is the window that is made of plexiglass. There is inside an artificial seawater, so it is seawater, but it has been, according to the standards, recreated in laboratory, so waiting the salts to artificially recreate the seawater for a repeatability of the tests. There is a continuous flow of the water during the tests to encourage the oxidation. Here there should be, if it works, a video that shows what happens during the test. The water is continuously flowing through a pipeline during the test. The specimen were kept in seawater for 24 hours before the test, and then the test was continued with inside the chamber with the water continuously rotating, moving around the specimen. This is another activity that we are doing, that are the quasi-static tests. These are simply some photographs of the specimens of the samples that were manufactured and needs to be machined to be tested in quasi-static conditions according to the standards. And so to conclude, these are the conclusions. To sum up, I can say that we're developing this this experimental campaign on this widely known material in corrosive environment and in air, in laboratory. And the interesting thing is that we are using a back phase strain measurement system that very simply, it's easier to be used because with one single strain gauge, you can appreciate the variation of crack length during the whole propagation, from the smallest crack length to the largest crack length with one single sensor. Thank you for your kind attention. So if you have any question, please.
So thank you for the presentation. Is there any question from the audience? Oh, I have a curiosity. Have you checked the crack path of the fatigue growth tests after failure? So it was tortuous or maybe planar?
Do you mean the crack surface after the in a corrosion test?
Also in the normal environment.
No. It is a simple geometry, let's say. So it's a CT specimen. It is standardized. So we just glue it to crack gauges at the two sides of the specimen, because it is so small that, let's say, just to verify that the crack length was measured, had the same length at both sides of the specimen. We did not observe the microstructure of the surface.
Okay. Have you planned also to investigate the threshold regime of the fatigue growth in both environment conditions?
No. It is a good question. It is a good point, actually, but we have not scheduled so far threshold tests.
Okay.